Hello, and thanks for watching. Today, we're going to discuss the AlloyDB vector indexing, and we will deep dive into the newly released Scan for AlloyDB index. My name is Yannis Papakonstantinou. I'm a distinguished engineer with Google Cloud Databases, and what I present to you is a short form of a presentation that we gave at Google Next 24 with Andrew Brook and Alan Lee. Let's first discuss why vector search is important in database applications, and then we will introduce the multiple AlloyDB vector index options, and we will deep dive into the scan for AlloyDB index. Finally, we will close with some statements about what is coming next. So let's start. Why vector search matters for databases? Well, databases matter because they are the trusted source that provides up-to-date data to your applications. And this has been for many decades. Nowadays, we have also enterprise data that is unstructured, product descriptions, conversation history, video clips, and so on. Now, SQL queries can start using this unstructured data by utilizing vector embeddings of this unstructured data. And then the embeddings are being queried with vector search. And that's where vector search and vector indexing become important. Now, AlloyDB is helping you in multiple steps of dealing with generative AI. Besides the vector indexing and vector search that we will discuss here, it also enables you to easily generate embeddings from your unstructured data and also manage them. It allows you to easily integrate with LangChain and Vertex AI extensions. And recently, we also announced the natural language for querying interface that allows you to easily build applications that can query the database with natural language. You can find more information about this in the blogs and other talks that from next 2024. But here, let's come back to the high performance and high scale vector querying. AlloyDB has gone into vector search since 2023 and offers a rich set of indexing options. First time in 2023, we supported the popular pgvector extension, including its HNSW and IVF-flat indexing methods. We also produced optimizations that accelerated 10 times the IVF-flat. This year, we continue with our commitment to pgvector, but now we also launched the pgvector compatible Scan for AlloyDB index that is complementing HNSW by creating superior performance and scale on multiple aspects that we will discuss later in this talk. All right, so let's go into looking into the Scan for AlloyDB index. Mechanics first. What is this? It is a new approximate nearest neighbor search index type, which is based on tree quantization. It is compatible with vectors of the popular pgvector extension. And in case you are new to the vector search area, the approximate nearest neighbor search is basically solving a problem, a fundamental problem of vector search. In order to do precise vector search, you have to basically compare your vector, your embedding, with every embedding in the database. So, for example, if you are looking to find out which image looks like a newly incoming image, you would have to compare the newly incoming image, the embedding of the newly incoming image, against the embeddings of all the images that you have in the database. And of course, this could take a lot of time and it doesn't scale very well. Approximate nearest neighbor search is basically saying you can do this much faster with an index. That is, you can quickly find the similar images at a minor recall, at a minor what is called recall loss. So basically, you can accelerate many, many times, like 100 times, 1,000 times, at a recall loss that basically says perhaps you will lose 1% of the top answers. And ANN is used nowadays everywhere. All right, now the mechanics. How can I create the scan for AlloyDB index? Well, number one, you are creating the Postgres ANN extension that we released. And then, assuming that you already have a table that includes a vector column, in our example, the vector column that you see on the screen is called embedding. It could be called anything. And then you're basically saying, I'm going to create a scan index on this embedding column for cosine proximity operations. As you may know, there is multiple kinds of distance. There is also, besides cosine, there is also Euclidean and inner product that we also support. Now, what were the goals for a scan for AlloyDB index? Well, our goal that we are committed, we became committed to it in 2023. We remain committed in 2024, and we will stay committed to it in the next years, is that we want AlloyDB to provide the best Postgres and SQL database vector search. Now, let's dive a bit deeper into what this statement means. What does it mean to provide the best? Number one, we know that you like the transactional semantics and strong consistency of AlloyDB and of Postgres, and thus our index is transactionally consistent with the respective data that it is indexing. Number two, it works fast for general OLTP workloads, which include read, write, update, delete, and of course the reads also involve vector search. And we should be clear here that it's not just works fast. The scan for AlloyDB is providing you a new state-of-the-art option that is exceeding the performance of pgvector HNSW in multiple cases that we will discuss next. So let's see these cases. So here is a data point. The scan for AlloyDB index can simultaneously achieve all of the following that you see here. 8 times faster index creation, 3 to 4 times smaller memory footprint, up to 10 times faster write throughput, and up to 4 times faster vector queries. All of these simultaneously. Now, let's discuss a bit more about where this is coming from after we first see a typical slide for those of you who have already spent a lot of time on vector search. This is the recall QPS, query per second / recall curve of the scan for AlloyDB index compared with the pgvector HNSW on the popular Glove 100 benchmark. Generally, up and to the right is better because it basically means that for a given recall, you can deliver higher number of queries per second, or for a fixed number of queries per second, you can deliver higher recall. Okay, now let's go into what is scan deep inside and how does it achieve these performance numbers that we discussed before. So before we discuss what it is, let's discuss what it is based on. It is an algorithm based on 12 years of Google research, and actually you have used it because it is the algorithm behind popular sites like Google Search, YouTube, Photos, and also the ads internally at Google. The algorithm has been open sourced in 2019 as a main memory operating library, and this, of course, happened much before we integrated to AlloyDB. All right. So scan is a compact tree-based index. Uh, it can have multiple levels, but here, for the obvious presentation simplicity reasons, I'm gonna be displaying only a two-level index. So on this two-level index that we see here on the screen, each leaf node contains a subset of vectors that are near each other, and each leaf node has a so-called centroid vector that is conceptually at the center of the vectors of this node. The centroids are the result of a learning procedure, which is basically a modified k-means algorithm. And what this algorithm is doing is it learns the centroids by minimizing the distance between the data points and their closest centroid. And that is basically what is creating the border lines that you see on the slide. This is basically the border lines that define which area its centroid is owning, in the sense that it is that its vectors are closest to it. Okay, now the HNSW, the PG vector HNSW algorithm belongs to a different family, the so-called graph-based indices. And it is worth understanding a bit about graph-based indices as well, in order to understand how the performance of scan is becoming better in multiple cases. So graph-based indices use a very different data structure. Each vector corresponds to a node in the graph, and given a query vector, when you're basically saying, hey, find images that are close to my query image, what is happening is that there is some entry points in the graph, and the algorithm starts moving to nodes, that is vectors, that are closer to the query vector, and it basically stops when it cannot find anything that is closer. Okay, so now based on this, you can see why scan has much faster index creation time and much faster writes. We are talking about a structure that is much more compact, that is basically you just have centroids connecting the nodes, as opposed to having multiple connections from each vector to each other vector. What is also expected here is that you're going to have lighter index overheads, that is smaller memory as well, and generally faster write time, much faster index build time, much faster insertion time. This is not something that is happening for scan for AlloyDB only. Actually, here we have plotted a bunch of well-known indices, and you can see that generally there is a trade-off between how good an index is on index build time versus how good it is on querying. Surprisingly, however, Scan is doing very well on both. So, how this is happening? And notice, your immediate expectation may be that graph-based algorithms should always do better in querying because they provide multiple paths towards the desired vectors as opposed to tree-based indices and algorithms that provide a single path to each vector. However, this intuition does not apply in multiple cases. Let's see, what is it behind this? Here is more precise numbers that you can download about performance of various indexing, but let's skip quickly to the explanation. Where is the performance is coming from? We will not have the time to discuss this very deep technology that has been developed over multiple years in the course of the few minutes that we have here, but it is worthy classifying it into a bunch of buckets. One bucket that delivers a bunch of performance improvements is quantization techniques. Quantization techniques both compress the original vector data set, but they also make the computation of distances between vectors very SIMD friendly, and thus more comparisons of the query vector to the database vectors can be executed per millisecond. The second part that is very particular to the scan algorithm and to the scan for AlloyDB is that unlike the graph-based algorithms, scan is very geometrically aware. That is, it does not simply understand the sizes of distances, but it really understands the relative positioning of the various vectors in the geometry and is exploiting the geometry in order to deliver higher performance at lower memory footprint. Finally, we discussed before that graph-based algorithms are basing their query performance on redundancy, on having basically multiple paths that get you to every desired vector. The truth of the matter is that scan for AlloyDB also has redundancy. That is, basically every vector is placed not on one centroid, not on one leaf node, but it is placed on two leaf nodes. But here comes the interesting thing. The redundancy of scan is geometrically aware in such a way that if the algorithm fails to find the first placement of a database vector, then the chances, the probability increases that it will find the second placement of this database vector. Notice, we're not talking about independent probabilities and saying here that, hey, at the end, one of them will stick. We're talking about some very geometrically aware placement that makes sure that if the first one fails, the second one has much higher chances to be found. Okay, so it is these reasons in a summary that converge to create the superior query performance superior to HNSW in multiple cases. I'm not making justice, of course, in 2 minutes on this deep research. You can learn more at the white paper that you see here on the slide. You just have to visit this and click, download it. You don't have to provide your name or anything. And the paper is readable by both people who are starting on vector search as well as experts. All right, so now putting it all together in AlloyDB, we took the scan algorithm and we have introduced it and integrated with the AlloyDB's paging system, thus delivering transactional semantics, strong consistency while maintaining the fast index time, the fast insertion, and the querying and the fast querying. The fast querying required also quite some work in order to create big contiguous layouts. And please read into the paper for the details of it. So let's summarize where we stand now and how we go forward. At the present time, AlloyDB gives you the richest set of native vector search options in SQL databases. We provide the graph-based pgvector HNSW, and as of this release, also the tree-quantization-based scan for AlloyDB, which, as we discussed, is superior to HNSW on memory footprint, indexing time, write throughput, and most usually also on query performance. Where do we go next? Number one, we are SQL folks. We know that SQL developers do not want to optimize queries. They expect the database to optimize the queries. They expect the database to optimize the indices. And that is what we are doing, auto-tuning of indices and queries. Number two, we have heard from our customers that they have vectors, but of course they also have structured data, and many queries involve both access to structured data and also the vector. So we are working on making these queries much more efficient. This is part of our broader portfolio on improving performance and scalability and in providing additional vector indexing functionalities. I hope that I had a chance to give you here a taste of the AlloyDB vector indexing portfolio and in particular of our Scan for AlloyDB newest release. For more details, you can go to our white paper, the Scan for AlloyDB white paper, and an easy way to find it is just go Google Cloud white papers, go to the top link, filter for databases, and then download the Scan for AlloyDB paper. You don't have to do anything. You don't have to provide your name or anything. Just download. I hope that you will read the paper and you will learn more about this exciting technology and the reasons for bringing your state-of-the-art vector indexing into AlloyDB.